Recall now that when looking at a continuous random variable, the CDF is found by integrating the PDF from negative infinity to some threshold y. It's the cumulative amount of probability up to that point. If you know the CDF, it is natural to wonder whether we can backtrack and figure out where we started from. What was the probability density function? And the answer is that yes, we can do this. This follows from the fundamental theorem of calculus, which tells you that integrating and taking derivatives are opposites of each other. So if you have the integral, or the CDF, and you take its derivative, you get the PDF. Consider the following example. Note that CDFs typically come in many parts. Usually there's a region with zero probability, and then probability starts accumulating. Perhaps it continues to accumulate forever. Perhaps there are a few gaps. The example that we're looking at here is a CDF where there's no probability before -2, and then it's growing from -2 to -1. It flattens out from -1 to 0, which means nothing happens because the cumulative amount is not growing. Then finally from 0 to 1, you experience the last bit of growth until 100% of all probabilities have been achieved. In particular, this shows that in this setting, the random variable is never before -2, but also never comes after 1, because the cumulative probabilities no longer grow. What if I want to find the PDF value at a half? I look down my CDF categories and notice that 1/2 occurs in the region that is highlighted here. So that's the region to work with when taking derivatives. Take the derivative of the CDF, and it will be evaluated at the point y equals 1/2. To differentiate a fraction like this, there are a few approaches that can be taken. The one that I will take is to break this up into parts. So I get 1/2 and y squared over 2. To take the derivative of each piece separately, constants don't change, the derivative is 0. Y squared over 2, the derivative as seen here, is a nice simple function, and we just get y. Substituting in y equals 1/2, you get 1/2. This same approach can be used to develop the full PDF from this. Before -2, the derivative of 0 is 0. Between -2 and -1, the derivative of y plus 2 over 2 is 1/2. However, notice that the way I wrote this, I did not identify what happens at -2. I had less than -2, and then I had something different. Why? The reason for this is that there's a discontinuity. When you take the derivatives of these functions, they don't agree on the left side and the right side. The derivative of 0 was 0. The derivative of the next piece was 1/2. At -2, I don't know what happens. Contrast this to the CDF. Notice in the CDF, one might say I was a bit sloppy. I had a less than or equal to -2 on the first line, but I included -2 on the second line as well. So what's the right answer? And the answer is they're both correct. If you put -2 into the formula, y plus 2 over 2, you get 0. So it was not necessary to tell which of those two lines reflects -2, just like it was not necessary to tell which one is for -1, and so on. But when we start differentiating, the endpoints are unclear. This is actually okay. You work with PDFs by integrating. If you get 1 point wrong, it doesn't matter because the area under a curve is not affected by changing a single value. It's only affected by changing pieces of the function. So when you work out the full PDF from this, you're going to have inequalities that don't include the boundary points.